Alright, so I looked around YouTube a little bit because I was looking to mess with some Triacs, and I couldn't find any video that showed you how changing a component would change the behavior of the circuit, or a simple waveform from an oscilloscope when you're messing around with it. So I decided to do one. I looked up this typical dimmer circuit, which you can find on the web. This is just one of the hundreds that turned up with Google Images. What they used and what I have is a BT137 for the Triac. I got one right here. The capacitor right here, I used a 0.1 microfarad, which is what they specified. We have a resistor here, which is basically there to limit current if you turn the potentiometer all the way down, so that the you won't overload the resistor or short circuit your 120 volts AC. And then your load is right here on your line. First thing you need to do is determine which one is the line, which one is the neutral. A simple test for that is to take a voltmeter and place one probe in the flat part of the socket, and the other end in the grounding plug. And if you have any voltage there, that is your line. If you have no voltage, try the other one, and you should. If you don't, you might have something wrong with your meter, so you want to make sure that you get one that's 120 volts and the other one should say 0. So once you determine which is your line, which is your load, you can go ahead and hook it up like this. And then what I'm going to do is I'm going to put an oscilloscope right here. Actually, I'm going to change that and put the oscilloscope right here. I don't know why I put there. That way you can see the waveform being delivered to the load. That's the Triac, Diac, capacitor. There's a current meter just to see what's going on here, and then the resistors. So basically the operation of this circuit, you're triggering a Triac with no external trigger. So you have voltage coming in here. You're going to have current limiting resistors, which determine how fast this capacitor is charged. And once this capacitor is charged to the breakover voltage of the Diac, it will allow current to flow and trigger the Triac. So basically a Diac, once it reaches that level of whatever the breakover voltage is for this diode, mine is a DB3. I think I got 40 of them on Amazon Prime for $7.13. Has a 32 volt breakover voltage. So at 32 volts, this will allow current to flow, triggering the Triac. Now, these resistors will affect how fast that capacitor is charged, and when that capacitor reaches 32 volts, it will trigger the Triac. So if you turn these way up and don't allow any current through, it'll take a long time for the capacitor to reach that voltage. Whereas if you allow as much current through as the limiting resistor will allow, you're obviously going to charge the capacitor much faster and reach the breakover voltage faster. So we're just going to take a look at that with the current meter, as well as looking at the waveform over the load as we vary that. We're also going to look at changing the capacitance and resistance and seeing how that affects the circuit and how you can tailor the circuit to your needs. So maybe you found this one, it was for 120 and you need one for 220 or 240. You can play with it and see how you can get the voltage you want out of it. Alright, so I quickly went ahead and set up the circuit. This is the oscilloscope hooked up across the load using these probes here. This is the current meter, which should read 0 to 10 amps. I might set it on a lower setting, seeing as it'll only be milliamps. Actually, let me go ahead and do that. Alright, since it's only milliamps, we're only going to see, I have a 10K in there, so you're only going to see about 12 milliamps, I believe. So here's our light bulb over here. We have mains voltage coming in here. I like to keep the plug unplugged when I'm not using it instead of using a switch. That way I can look over and visually see that there's no power to the circuit. And then here I have a 100K potentiometer. So I'm going to go ahead and plug this in. Let me turn the resistance all the way up. Go ahead and plug it in. So with a 100K resistor turned all the way up, the minimum voltage that you're going to get on this load, this is a 25 watt light bulb, you're going to get 95 volts. That's RMS. So that is the lowest you can dim the light bulb yet. Now the light bulb is pretty dim, but I would like to go lower. Now I'll just show you real quick using the potentiometer to adjust the brightness. And we can, I'm going to decrease the resistance, and as we decrease the resistance, you see that more of the waveform should be visible. So as it gets up there, it's at 120 volts now. So it's fully activated, even though you see a little bit left over there. It's fully activated by that potentiometer being turned all the way down. Now that got switched to DC. Now that's 10.55 milliamps that it's drawing right there. So it's putting, well, almost 11 milliamps through that resistor. Now if you do the calculation, if that's a 10K resistor, then you have 11 squared times 10K. You got 1.21 watts. Now that's a 1 watt resistor, so if we left this going, that thing's going to heat way up and maybe even start smoking. So as we turn it down a little bit, we're going to get less current through there because we're increasing the resistance. Now, I didn't really like the circuit. I like the overall circuit, but I don't like the values because it only lets you get down to about 96 volts, and I want to be able to turn this thing off. And go all the way down to 0 volts, come all the way back up to 120. So what we're going to do is we're going to increase the capacitance by adding another 0.1 microfarad capacitor in parallel, which is going to increase the capacitance across that junction to 0.2 microfarads. Now what that does is by increasing the capacitance, you're going to increase the charging time required to reach that breakover voltage. So we should see a decrease in voltage when the resistor is turned all the way up. So let me go ahead and set that up and we'll try that. Alright, I don't know if you can see it there or not, but I have two 0.1 microfarad capacitors now hooked up in parallel to form the 0.2 microfarad capacitance. So now if we go ahead, we'll turn this all the way up so it's in the off position. We'll plug that in, and now I can barely see that filament in that light bulb. It's just barely glowing, and if you look at the oscilloscope, you'll see it cuts that waveform off almost at the end. So we're still getting some voltage with it turned all the way up, but it's very low. So I would almost be okay with that because that's going to be low enough that if you wanted, you could obviously turn the switch on or off, and then the dimmer would allow you to adjust the voltage all the way down to 34 volts. Now let's see if we increase. Now obviously we have not changed that limiting resistor, so this current should not change. And indeed we're seeing about 10.5 volts again. 10.5 milliamps across that resistor right there. But we're seeing 118.9 volts RMS, so we're only 1 volt under mains voltage. So that's excellent. That would allow for a lot more variation and voltage control by just simply adding one more capacitor. You could also somehow, maybe if you could find a 0.2 microfarad capacitor, you could use that, but it's not a common value, so it might just be easiest to use two 0.1 microfarad capacitors. That's just slowing it down, and so you can get that lower voltage. What I want to do now is I want to add a third one in parallel, and I want to go ahead and see if that allows us to reach that full off state. So I'm going to go ahead and add one of those, and we're going to try this again. Alright, I went ahead and attached that third capacitor. You should be able to see 3 little capacitors here. And again, those are all just across C1. Let me grab this here. So if you're looking at this voltage diagram, those are all just going to be in parallel across the diac and neutral. So we're not changing anything in the circuit. We're simply adding capacitance to that junction. So I'm going to go ahead and plug this in, turn that all the way up to the off state, plug this in, and sure enough, we are getting 5 millivolts across that, and it's actually at 20 megahertz, so that's just noise on that line. So we do have 1.35 milliamps across that, which if you do the math, that would be 100K, and that is a 10K resistor. So you have 110K, and then you'd have 120 divided by 110K. And that equates to 1 milliamp, 1.09. So that's about what we'd expect across that, given the variation in resistors that you can get. So if we go ahead and turn this up a little bit, so I think, let me turn that back down, see how low we can get that thing. To 37, 30, 25, 23, 22, 21. That went to 17 before we zeroed out there. So I'm going to go ahead and turn that up. As you can see, this is a nice dim bulb. I don't know how well the camera will portray it, but I'll move it over here so you can see that a little bit. Basically, that's barely glowing. I can see the filament in there. Again, I don't know how well the camera will show that, but I can see the filament. It's barely glowing. It's a nice soft glow. Now, if I turn this up, and that's at 60 volts, so that's about half of what your normal voltage is in your wall. So if you turn this up, we're starting to see 5 milliamps across that resistor, and we're all the way up to 107 volts. And again, that's RMS. And we start to see the waveform filling in here as we get way up there. And I turn that all the way down. We're going to see 117 volts across that. So we have about a 3 volt drop from mains voltage, but with the control that this gives you, I'm really not too concerned about it. But what you could do if you wanted to see a little higher is you could decrease that current limiting resistor and go ahead and see what that does in terms of the maximum voltage that you can get out of it. So I'm going to go ahead, that's a 10K right there. I'm going to go down to just 9.4K and see what we get out of that in the max voltage range. So I'm going to go ahead and do that. Alright, I went ahead and added 2 4.7K resistors in series to give you that 9.4K. Now, I'm going to go ahead and plug this in, and we're going to see how high we can get the voltage, because we know with this capacitance we're able to go down to 0. I'll show you that again real quick. If we turn that all the way to the right, we do indeed get 0 or 5 millivolts, which is just noise. So as we turn that up, we can get to that dim voltage of 60 volts. And if we go all the way up, we can get to, it's only still going to about 117. We gained about a half a volt. Now we're at 12 milliamps. So 12 milliamps across a 9.2K load is going to give you a dissipation of 1.3 watts. Now these are 1 watt resistors, but because they're each 4.7K, you should only see about 0.65 watts across each resistor, which they can handle. So this is an okay circuit. You go up to 117 volts, all the way down to 0, but I'm not really sure it's worth going down that little in resistance. So I'm going to go ahead and change that to just a 6.9K resistor, which is actually going to be a 4.7 and a 2.2 in series, and we're going to see what we can get out of that.